Hi, I'm Kaylee,
I'm Chloe.
I'm Shrishta.
I'm Talia.
I'm Manisha.
and we're working with Medtronic to develop Stingray, a vagus nerve stimulation device for stroke. Every 40 seconds, someone in the United States has a stroke, which can affect the entire body and significantly decrease quality of life. Current therapies aim to improve the brain's neuroplasticity, a driving factor in improving therapeutic results and reducing recovery time. One example of this is vagus nerve stimulation, also known as VNS. VNS increases the brain's neuroplasticity and reduces cerebral inflammation. However, current VNS devices are invasive, difficult to use, and lack a feedback loop.
Now I'll move on to our market strategy, and here is our value proposition. Our device provides therapy to stroke patients through a non-invasive, simple to use, and more effective feedback loop. We surpass our competitors, which have invasive devices that are less likely to produce long-term results. The market size for stroke management will hit $65.45 billion by 2030. Our device targets all stroke patients, which includes nearly 800,000 people annually. The current market size for VNS in the United States is 277 million and is projected to increase with a compound annual growth rate of 18%.
Moving on to our approach, we're creating a neck collar with built-in electrodes for current stimulation and an electromyography or EMG device to gather electrical feedback. The electrodes will emit a current onto the vagus nerve, causing vibrations in adjacent muscles. The EMG will collect the signal generated by the muscle and send it back for analysis. We are using the MyDAC function generator to produce voltage that will be converted to current for the electrodes. The circuit that we are going to use to convert the voltage to current is the Howland current source. These are images of our prototype so far. The image on the right shows our neck collar completely set up with the electrodes and EMG.
Our device incorporates a feedback loop, which ensures that the vagus nerve is being adequately stimulated, a feature that sets us apart from competitors. For our design criteria, we're focused on the collar's weight and dimensions, the distances between the components on the inside of the collar, and the amount of current emitted by the electrodes. Research has shown that the infarct volume and cerebral inflammation are reduced when the laryngeal muscle is emitting a voltage of 0.3 volts, making this our target output voltage.
First, we'll test the circuit using a multimeter so that if we input a certain voltage, we receive the desired current output. Next, we must verify that we receive the expected output from our electrodes. We'll connect electrodes to our circuit, then use a multimeter to measure the output. We want to make sure that device functions as a whole in a real-world setting, where we know skin and muscle impedance can hinder the effectiveness of the therapy. Ballistic gel is the closest artificial flesh substitute that mimics the impedance of human flesh. Our setup involves creating a pseudovagus nerve, which is a wire embedded in our ballistic gel. To test the impedance of the skin, we will place our electrodes on the surface of the ballistic gel. Then we will use a multimeter to measure the current output at the wire. Thank you, and that concludes our presentation.